All right. Well, we have been leading up to this for quite some time. We are finally going to have be able to write compounds and formulas. That's right. And there was much rejoicing. Oh, that was good. Chemical formulas and compounds. We're going to use our knowledge of the past 3 or 4 chapters to be able to put together compounds into their. I told you before. I said that we're heading for this a couple of times. Why is water H2O? You know, why is sugar C6H12O6? Why is salt NaCl? Well, now we can do it. We can do that. We're going to learn how to do it without writing out all electron dot notations, without what you just did in that test. We're going to shorten it up so we can just write the formulas very quickly. Okay? And I don't have a lot of notes to give you. They're almost all examples. We'll start with naming and writing binary compounds. How many elements do you think are in a binary compound?
2. Yeah.
Mm-hmm. And these are probably, it's a funny thing. I say that these are the easiest ones, and yet it's so funny because we'll end up making crazy, stupid mistakes when naming these easy ones once I teach you how to name the harder ones, because they're named differently. They have different suffixes and stuff, and it turns out that when you're going to be watching this and say, wow, I can't get this wrong. This is so easy. And then it's like you get some new information and you start to name them a different way. Okay, you're going to have to keep things straight in your head because we're going to really learn about 3 different kinds you can name. 2 kinds of binary, and then 1 kind of ternary. I'm not going to do a ternary today, the ones that have 3 elements in it. I'm going to do those tomorrow. But just doing the binary ones, even those you can mix up if you're not careful. All right, let's talk about these binary compounds. We'll start with if we have a metal together with a nonmetal, which is the most likely combination you're going to see, because everybody gets happy that way. You know what happens when a metal and a nonmetal get together. You usually get an ionic compound where one guy wants to lose electrons and the other guy wants to gain. And our classic example of that is probably salt, which we call what? What's the name of NaCl? What's the name of it? Sodium.
Chloride.
Yeah, you notice you just said it. You just said sodium chloride without me ever teaching you. That's all you do in naming these. You simply name the positive ion, sodium. You name a negative ion, chlorine, and you add the suffix. You change the suffix to what? Ide. That's what you do every single time. Okay? Name the positive ion, name the negative ion, and then add an IDE suffix. So you already know how to name that. The thing is, everybody's named the same way. If you know how to name sodium chloride, guess what it is when it's sodium and fluorine together? What's it going to be? Sodium fluoride, sodium oxide, sodium nitride, potassium fluoride, potassium oxide, potassium nitride. That's all you do. It's that simple. And here's a couple of examples. I'm actually going to do more than a couple because it does get harder if you're doing them backwards. Okay, so let's do some examples. Ready? NaCl, our classic example is, of course, sodium chloride. No one's going to have trouble doing that. Okay? Everyone's going to do that right. I'll throw some, guys, when it gets harder is when you do them backwards. But we'll do some other ones of this. Okay. For example, don't be confused by this. Write that guy down. Li3N. I know, oh, there's 3 in there. What does that mean? Like tri or whatever? No. Li3N is a binary compound. And hence we name it the same way we name this guy. What's his name going to be? Lithium nitride. Not nitrate, not any other crazy name. Lithium nitride. Sodium chloride. That's all you do. But what about the 3? It means nothing in these kind of problems. We're going to learn where it does mean something. You're going to see that. All right, this guy is lithium nitride. Okay? So don't go trying to use the numbers, and don't go changing the subscript to some other crazy name. Like, for example, do you really think it's going to be called, and I know someone will do this, lithium nitrogenide? It doesn't even sound right, right? Just like you didn't call it chlorinide, you called it chloride. You change the suffix, right? Same thing here. Lithium nitride. Study. All right, so when does this get more difficult? Well, if I give them to you this way. Why? Well, you'll see in a second. Write that guy down. If I give you the name and I ask for the formula, you're going to have to worry about something. Something that was done for you when I gave you the formula, but something that's not done for you when I give you the name. I got to know how many of each element to use. Now, on the test you just took, you know what you did. On the test you just took, you wrote aluminum's electron dot notation. You said, what does he want to do? You looked up fluorine's electron, you see what he wants to do, and you put them together. We're going to shorten that up a lot. We don't want to have to do that whole chart every single time I write a compound. That's crazy. So I'll just write aluminum, and I'll write his charge. And I can tell his charge without writing electron dot notation just by looking at the periodic table. Look at the periodic table. Where is aluminum in the periodic table? Group 3. See it? What side of that line is he on? The left. So what does he want to do? Lose how many? Lose 3. So how about plus 3 charge? So I simply write that above it. Do that for aluminum. How about fluorine? Where's fluorine's in the periodic table? Where is he? Yeah, so he's going to gain how many? 1. So what will his charge be? -1. Now, all you have to do is just a short way to do these. Notice I'm using the exact same logic I used in the test you just took and in the previous chapter for the octet rule. The same exact logic applies. That -1 means he wants to gain an electron. That +3 means he wants to lose 3 to get an octet. All of that's still used. But it's a lot simpler now. If I just write the charges down, I balance it out. How can I balance those charges out? What do I need? How many F's do I need to make them equal? What do I have to do? 3, right? Because 3 times -1 is a -3 and a +3. They're both equal and opposite. They're 0. That's exactly what you do. Isn't that nice? Pretty easy. So that's why the formula for aluminum fluoride is AlF3. Okay? You say, well, why didn't I do that up here? I didn't do that up here because you're already given it. You were given Li3N, NaCl. You were given that, so you just had to write the name. But if you're given the name, you've got to write the formula correctly using the right charges. Let's try another one. Calcium oxide. Now, we have actually done calcium oxide and aluminum fluoride last chapter. We did them at electron dot notation. You don't believe me? Go look them up. Okay? Matter of fact, we did sodium chloride. We did almost every one I'm going to do up here last chapter. But now we're doing them faster. We're going to write calcium with his charge. Look where calcium is. In the periodic table, he's in group 2. He has 2 electrons in his outer shell. He'll have a +2 for a charge. Everybody agree? Right? Look where oxygen is. Where's oxygen? Group 6. What does he want to do? Gain 2. What would his charge be? -2. So you can gain 2 electrons. You get a -2 charge. Do I need to add any subscripts to this guy? He's good. And by the way, that's what we call these guys. We call these guys subscripts. And not to be confused what we're going to call coefficients. Both of those words you've heard of before, but in chemistry they kind of mean something different. Coefficients go in front of formulas. Subscripts go underneath elements. All right? And they kind of mean different things. As we go along, I'll explain how you apply them. Kind of has to do with like math. We would have a coefficient in front of something. It's very similar to how a coefficient works in this. We really get to that under reactions. All right, let's try this one on your own. If you can do that one, you're doing okay. Then I got one more tricky one to do. Actually, 2 more tricky ones. A little twist to throw at you. Sodium nitride. If you do that one on your own, I know you can. Take a look. Find in the periodic table. Find sodium. Find nitrogen. All right, let's see how we did here. Marie, what is the symbol and charge of sodium?
Na+1.
Correct. Nitride. What's the symbol and charge, Kate? What of nitride?
N-3.
Right. Put the two together, balance them out. What do I need? Everybody agree? Because 3 times 1 is a positive 3 and a negative 3, and they'll equal 0. You got to balance them out. Okay. Perfect. Now, what about a guy like this? Can you handle it? Can you handle it? Say, well, it's going to be the same as the other one. Well, a little different. That was my invitation to Marie. Well, she says that a lot. You ever notice that?
Never said that.
Well, me too. You've never said that. Hannah's laughing at you. She scoffs at you're never saying that. Well. Okay, you're trying that one on your own. And he has a little twist to him. It's not a biggie. It's something you can remember from math class. You have to find here. I don't think you're going to have too much trouble with this, but just in case, let's write them out. Everybody agree Mg has what charge, Katie? Thank you, Katie's voice has gotten much deeper. It's all that chocolate she's not been eating. Phosphorus has what charge here, Katie?
-3.
-3, that's better. All right, now I got +2 and I got -3. There's a problem with this one. There's no one number I can put next to P or Mg that's going to help me out here. So what do I do, Anthony?
3 magnesiums and 2 phosphorus.
Exactly. Least common multiple, right? You've heard of that. LCM or LCD, if it's a least common denominator. Basically, the least common multiple of 2 and 3 is 6, right? So 3 times 2 is a +6. 2 times -3 is a -6. Got it? All right. Last one, which shows you something you're going to see in the homework tonight quite often.
I said last one like 10 times.
I was wrong. And I couldn't have said it 10 times. I only have 6 examples on the board. Exactly. So let's not exaggerate much. This is 10 times. I said it twice. All right. Now, here's the problem with this guy. Iron bromide, iron 3 bromide. You see, guys in the middle, I told you about this before. Guys in the middle of the periodic table, we had no way to really predict their charges because they have multiple charges. See where iron is in the periodic table? All right, look where he is over there, right? That's a problem. Okay, I don't know what his charge is, so I have to tell it to you. Right there. What do you think the charge is for iron in this case? +3. Exactly. So I'm going to have iron with his +3. And what's the charge for bromide? -1.
So you're going to do 3.
And so what will I need? Yeah, Br3. Now, people see that Roman numeral 3 here, and sometimes they misinterpret that to mean it's Fe3Br. See, that's wrong. The 3 applies to the charge of the Fe. It's FeBr3. Got it? All right. So let's do one more. It's got the last one now. That was a joke. That really was the last one.
There's another one.
That was the last one. All right. Now, that's how you do the very, very simple metal, non-metal ones. It gets a little bit more difficult when I throw in the name first, and you got to write the formula, but just using the charges, you can do that. Now, the second type are when you have 2 non-metals together. And these, you can look at it one way, they're actually easier than the other ones. And in the other way, they're a little bit harder. Okay? Look at that explanation of what to do. Kind of sounds like what you just did, doesn't it? Name the first element, name the second element, then add IDE. It's exactly what you got done doing a minute ago. We have one more thing to add to that little statement, though. When you're dealing with 2 nonmetals, you can't really predict the charges. You have to kind of know which ones they are. You have to kind of know which compound you're talking about. Often there's more than one. For example, again, remember last time I used my first example, I used NaCl as my first example. Okay, don't write this down. NaCl was my first example, and you all called him sodium chloride. And I said, that's the exact same way you name everything. All right, and we did. Lithium fluoride, sodium nitride. That's the same way. Can you name two nonmetals together? Look at this guy. That's a nonmetal. That's a non. They're both on the left side. See, I'm both on the right side. See it? They're both nonmetals. What would you just naturally call that guy? Carbon dioxide. And you would just naturally call him what? This one. Carbon. What kind of? Monoxide. You've heard of carbon monoxide. You just, if you've been paying attention to the news, there were just 2 people killed in a mine in Colorado from carbon monoxide poisoning. And then there was a school, I think in Massachusetts, where like a whole bunch of people were in the hospital from carbon monoxide poisoning. You hear about that every winter when they start heating. Apparently no one watches the news around here. But my point is this. What did you do differently, Nick? Did you call this sodium monochloride? No. You just naturally did it for these two. And that illustrates the difference between these kind and that kind. When you have 2 nonmetals together, you have to tell me how many there are of each. So we're going to use a prefix to do that. Okay? You say, well, why do you have to do it there and not for the metals and nonmetals? Well, the reason is when you put 2 nonmetals together, they often do combine in multiple ways, as you can see with carbon monoxide and carbon dioxide. And so I have to tell you which one I'm talking about. I can't just automatically assume carbon has this charge or that charge like I do with sodium and fluorine. I kind of assume their charges. Here I have to be told them. So we use the prefixes. Now the prefixes are in the book, all right? And you can look at what page they're on. I think it's page 212. I think they write that down. I think it's on page 212, all right? But before you even open to that, let's see if you can figure out some of these prefixes. What do you think 1 is? Mono. 2? What do you think 3 is? Tri. Now 4 is the one everybody gets wrong. It's not quad or quattro. It's tetra. Tetra. But 5 you should know. What's 5? Pent. 6. Hex. 8. Oct. 9. Non. And 10. Dec. The other one that I heard somebody actually skip ahead to 7. That's always I say that one for last. It's always a tough one. 7 is what? Hept. Yeah. So if you don't know those prefixes on that page, you'll have to know them for the test. But most of them, you obviously, having never taught them to you, you knew all but probably 4 for tetra and 7 for hept. Everybody knows 8 means oct, right? Oct means 8. Everybody knows di is 2, tri is 3, mono is 1. Everybody knows that. I mean, there's a handful you might not know. Hex, hept, tetra. Everybody knows pentagon, right? Pentagon is 5. So there's a few you may have to look over, but for the most part, you know these. All right. Let's do some examples. Maybe it's page 151. Well, you'll have to write down and see which one it is. I thought it was 212. I've written here 212 and 151 here. You know what I'm betting? I'm betting 151 is correct because that's where the homework comes from. So that's where the actual table is, page 151. Again, you don't really need to open to that right now because you're going to know most of these prefixes anyway. All right, let's do some examples. CO2. What do you think that guy is? Carbon dioxide. Now, some of you might be thinking to yourself, well, do I need to use the prefix in front of only the second one? Actually, no. You kind of need to use it everywhere with the exception of if the first one is just 1. So that's why this guy could be called carbon dioxide. But if there were, say, 3 carbons in here, I would have to call it tricarbon dioxide. Okay? Let's do some other examples and you'll see. Try this one. What do you think that guy's name is going to be? N2O5. What do you think? Dinitrogen? Dinitrogen. Dinitrogen. 5 is pent. Oxide. Dinitrogen. It's like a horror movie. Pentoxide. Dinitrogen pentoxide. And by the way, somebody might say, well, is it pentaoxide? Or because if you look in the book, it says penta is the prefix. It depends. I mean, you keep the penta if it's usually if it's a suffix in that. I mean, not suffix, a consonant in the next letter. So pentasulfide, you would say. All right, but if it's a vowel, you usually drop the a. So you don't say pentaoxide. You say pentoxide. I probably won't take off either way. Okay. Try another example here. Now, doing these backwards is funny. Not ha-ha funny, but curious funny. This is actually the easier way to do these for these kind. The ones we just did, the metal, non-metal ones, it was harder to do this given the name and trying to get the formulas. But for these guys, it's actually easier. I don't need to look anything up, people. Carbon disulfide tells me what to write. What do I write? CS2. That's it. So all you people I saw out there, and I saw you, looking up at the periodic table, all right, what's the charge of this guy? What's the charge of that guy? Forget about it. You don't need it. You're never going to need it. All right? It's going to tell you it in its name. Okay? There's no way you can predict some of these without being told it. That's why we have the prefix in there. Check it out. One more. Going the other way. P4O10. This is the last one. It really is, though. That's about as hard as it gets. I think you can answer this one. You can answer any of them. Try that guy. Remember what I said about 4? Okay, if you remember that one. Mentioned it a couple times. You should think of the game. Remember the old game with the little pieces? You said they fell and you had to match them up. Remember they were like they were like this, like maybe one like that. Remember that one? And then there was one. There was just 4 of them together like this, right? Do you know what that was called? Tetris. Do you know why it was called Tetris? Because every one of them was a variation of 4 blocks. Tetris. You never figured that out, did you? Look at Caitlin. She's like, oh my God. Yeah. Look, remember the ones that were like this? There was it's just like that, right? And you flip them around and you fit them together in a puzzle. Every one of them was 4 blocks, and you guys never figured it out. Remember this one? Yeah? He was my favorite right there. That was my favorite Tetris. What else was there? Oh, yeah, that's right. There were ones like this. That's right. It was called Tetris because they all had 4 blocks. You're all like, oh, my God. This is so cool. This is the best thing I ever learned in chemistry. Anyway, what do you think the name of this guy is? I just blew Hannah's and Caitlin's mind. God, they're ruined for the day. Did you figure that one out, Michael? Did you know?
No, but I tend to in history class just make up stuff to say that sounds intelligent.
Mm-hmm.
It's great. It's great.
Well, now you got something that actually makes sense. All right, what do you think P4O10 is? Come on, somebody's got to tell me what P4O10 is. What do you think?
Tetraphosphorus dicoxide.
Tetraphosphorus dicoxide. Well, that sounds impressive, doesn't it? It sounds like you know what you're doing. Tetraphosphorus dicoxide. That line wasn't supposed to go through. It was supposed to come underneath it. Right. Absolutely. And that's the last one. Thank goodness. All right.